The objective here is to use the Sieve of Eratosthenes to find prime numbers. This is a concept that should be one of the first things introduced is very hard. This problem is called prime factorization, and finding an algorithm which does it fast is one of the unsolved problems of computer science. So if you hear anyone talking about prime factorization, that's what they are talking about. If you're a fan of pseudocode, here is the pseudocode to create a way for a computer to go ahead and output prime numbers. Here it is in Python. So you start with a variable called primes, and you'll make that an array. Then you'll create this loop, and this particular one will only look for prime numbers between 2 and 21, as you can see by the output down here. So if a variable is true, then you're going to look at a number in the range of 2 to 3, and then 2 to 4, and then 2 to 5, and so on. And if that number modulus by the number in your range results in a 0, then the isPrime variable will be false. So anyone not familiar with modulo or modulus operators, these are basically just remainders. So if I take the number 2 and I divide by 2, I get 0. So if I take the number 4, let's say, so if 4 divided by the number 2, that's just one of the numbers in the range, right? So 4 divided by 2 is 0, so therefore 4 is not, it's false, 4 is not a prime. But if I take 5 and I divide by 2, the remainder is 1. So since it's not 0, it's going to be true right here. And then down here, I'm saying that if the isPrime is true, then I'm going to take that number right here, 5, right? It's right here, 5, and I'm going to append it to a list. That list or array I'm calling primes. And if I hover my mouse down there, it'll pop up this annoying thing, but you can go ahead and see that number 5 was in there. So then you can kind of just mentally keep going through this Python code to see if each number between 2 and 21 is correctly being identified as a prime or not. So now let's play around with the whole public key encryption idea to better value prime numbers. Now the classic example everybody uses is Alice, Bob, and Eve trying to communicate. Well, not Eve, she is the eavesdropper in this scenario. So Alice and Bob, they are of course just substitutes for some of our everyday encryption needs. Like maybe you're trying to sign into your bank or sign into Facebook. Like in these scenarios, the person trying to sign in is Alice, and the person communicating with Alice to make sure she is who she says she is, and she is deserving of the secret to unencrypt the data. Bob is in charge of determining that. So this is going to be a little rough, but just try to hang with me here. It says as Alice goes first, she'll choose a prime number to act as a modulo operator, and then she picks a private number to compute a third public number, and at this point she has 2 public numbers. She will soon be able to tell what Bob chose for a private number, once he gives her the result of his computation involving a prime number, that is. The way he'll do that is by creating his own private number and then using the first public number to multiply by his private one and then mod that by a prime number they agreed on in the beginning. So I hope you're just patient with me right there as I was reading this thing about Alice and Bob. I just am trying to emphasize the importance of primes. You saw how often the word prime number popped up there. So if you go to this link here, and you have to have a code.org account to be able to play with this widget, but the widget is called the Public Key Cryptography widget. And I like to choose all right here just so I can demonstrate that narration of choices I just gave you from Alice right here and Bob right here. So let's say Bob's the bank, Alice is the user of the bank, so she's going to go ahead and choose a prime number. Let's give her 11. Now she gets to choose a private key, so I'll let her choose maybe 7. Let's go with the big one there. So after choosing these 2 numbers, we are given the public key of 8. So I can go over here and put in 8 for Bob. 8 is also a number that Eve knows. This number is not a big deal, but this number was generated by a relationship between these 2 prime numbers. Now that Bob has the information he needs, these 2 public numbers from Eve, once Bob chooses a secret number, he will then calculate another public number. So he'll take 5 and he'll take 8, times them, then divide them by 11, and his result is going to be the number 7. So we go over here, Alice puts in 7. This is a very special number because he used a secret number and these public numbers to come up with it. She'll go ahead and do 7 times 7, so that's her private and his private, or public, sorry. See how confusing this gets? So when you times 7 by 7 and divide by 11, the remainder you get is 5, and that was the private number of Bob. So if this was a simple Caesar cipher, we now know that 5 is what we needed to shift the alphabet by, and we could decrypt the bank data that Bob is sending us about our own account. Okay, so this definitely was not a lesson all about public key crypto. If you want to learn more, here's some links I suggest you go to. I especially liked the Khan Academy one. But remember, the point here is you could use this sieve to find prime numbers, and prime numbers are especially important. And so if you're a visual learner, just always thinking of this modulo operator plus the concept of prime numbers equals happiness and love and this whole magical, amazing thing we call public key encryption. This is how we secure privacy on the internet, and the way we make sure people can't pretend to be us on the internet. Well, to an extent, that is. And I hope you like my little thing of cookies down here, just as a reminder that this almost division sign, I mean, it's a percent sign, isn't it? If you squiggled that line over or push that line over, it'd be a division sign. All this is just a remainder. And instead of reporting back on the 3, reporting back on what it was divided by, it's reporting back on what the remainder was. And again, these two working together is just creating this cool magic. So that was it for today. How high can you go with your Sieve of Eratosthenes? And then just please tell me why primes are useful to computing.